influence. We use electricity for almost all the appliances at home. Lights, fans, the television, the music system, and the computer all run on electricity. Electricity drives our world. Electricity is also known as electric current. In this lesson, you will learn about electric current, its causes and applications. At the end of this lesson, you will be able to identify the features of electric current, explain how potential difference generates electric current, define electrical resistance, identify the factors affecting resistance, and state and apply Ohm's law. Before learning about the cause and applications of electric current, let us examine the features of electric current. Typically, in a conductor, free electrons move randomly. When these electrons are influenced to move uniformly in a specific direction, we get electricity, or electric current. The direction of electric current is the same as the direction of flow of electrons. Electric current requires a continuous path of conductive material to provide a conduit for electrons to travel through. Electrons move in the empty spaces within and between the atoms of a conductor. As each electron moves uniformly through a conductor, it pushes the one ahead of it. Thus, all the electrons move together as a group. When you unplug an appliance, say a toaster, from the power supply, the flow of electrons is interrupted and the appliance stops working. You can measure electric current as the rate of flow of charge, or the amount of charge flowing through a point per unit time. Electric current is measured using an ammeter. The standard metric unit for current is ampere. Ampere is often shortened to amp and is denoted by the unit symbol A. 1 ampere is equal to 1 coulomb of electric current per second. Electric current is a result of potential difference across 2 points in a conductor. Potential difference is the difference in number of negative charges that leads to flow of electrons. Electrons flow from negative potential, that is, the point with more electrons, to positive potential, that is the point with less electrons. Whenever there is a potential difference, the current flows from the positive potential end to the negative potential end. Numerically, potential difference is the work done in moving a unit charge between 2 points in an electric field against the force of the electric field. Potential difference is measured using a voltmeter. Potential difference is often referred to as voltage and is represented by the letter V. If the work done to bring a charge of 1 coulomb from one point to another is 1 joule, then the potential difference between the points is 1 volt. As against potential difference, potential is the work done in bringing a unit charge from infinity to a point. Thus, if the work done to bring a unit charge from infinity to a point is 1 joule, then the potential at that point is 1 volt. In the given example, potential difference between points A and B is the difference in the work done in moving a unit charge from point A to B. Conductors can be in solid as well as liquid states. In solid conductors, positive ions are immobile, and only the negatively charged electrons flow from high negative potential to positive potential. This flow of electrons is known as electric current. In liquid conductors, the current is caused by the flow of charged particles in both directions at the same time. In addition to potential difference, electric current is impacted by another factor called electric resistance. The electrons in a conductor do not travel in a straight path from one end to the other. While moving across the conductor, the electrons collide with fixed atoms within the conductor, encountering hindrance in their movement. This hindrance or opposition to the flow of electrons is called electric resistance. While the electric potential difference between two terminals encourages the movement of charge, resistance discourages it. Thus, the rate at which charge flows from terminal to terminal is the result of the combined effect of these two quantities. The standard metric unit of resistance is ohm, represented by the Greek letter omega. When 1 ampere current flows through a conductor across a potential difference of 1 volt, its resistance is 1 ohm. Resistance to charge flow within a conductor is affected by some clearly identifiable variables. First, the resistance of a conductor is directly proportional to its length. The longer the conductor, the more resistance it offers. After all, if resistance occurs as a result of collisions between electrons and the atoms of the conductor, then there are likely to be more collisions in a longer conductor. More collisions mean more resistance. This relationship between resistance and the length of the conductor is termed as the law of length. Secondly, the resistance of a conductor is inversely proportional to its cross-sectional area. Larger the area of the conductor, lesser the resistance offered. This relationship between resistance and the area of a conductor is termed as the law of area. The third factor that affects resistance to charge flow is the material that a wire is made of. Some materials are better conductors than others and offer less resistance to the flow of charge. For example, silver is the best conductor. However, silver is never used in wires of household circuits, as it is expensive. Copper and aluminium are among the least expensive materials with suitable conducting ability to permit their use in wires of household circuits. The conducting ability of a material is often indicated by its resistivity. Resistivity of a material is the resistance offered by a conductor having unit length and unit area of cross-section. The resistivity of a material depends upon its electronic structure and its temperature. The fourth factor that impacts the resistance of a conductor is temperature. For most materials, resistivity increases with increasing temperature. The variables affecting resistance can be mathematically written as R is equal to rho L divided by A, where R is the resistance in ohm, rho is the resistivity in ohm meter, L is the length of the conductor in meter, and A is the cross-sectional area of the conductor in meter square. In 1827, a German scientist, George Simon Ohm, conducted a series of experiments to study the variations in electric current when the potential difference across a conductor was changed. With the findings of his experiments, he postulated Ohm's law, which explains the relationship between electric current, voltage, and resistance. Ohm's law states that electric current through a metal conductor in a circuit is directly proportional to the potential difference or voltage across it, and inversely proportional to the resistance between its ends. Thus, according to Ohm's law, voltage V is equal to the product of electric current I passing through the conductor and the resistance R offered by it. Let us use an example to see how these equations help us analyze simple circuits. In the given circuit, there is only one source of voltage, a battery with 12-volt EMF, and only one element of resistance to current, a lamp with a resistance of 3 ohm. Using Ohm's law, you get the voltage in the wire as 4 ampere.